Hello everyone. In this session, we will see about what is NP hard and NP complete classes and the examples considered under NP hard problem. So starting with the introduction about the classes, as we have seen in the last session itself, P is a set of all decision problems solvable by deterministic algorithm in polynomial time. So we have seen that what is deterministic algorithm in an earlier session. So a problem that is NP hard or NP complete has a property that it can be solved in a polynomial time if and only if all other NP complete problems can be solved in a polynomial time. So basically the distinction between the problems that can be solved by a polynomial time algorithm and a problems which no polynomial time algorithm is known. So it is unexplained phenomena that for many of the problem we know and study, the best algorithm for their solution have computing their time that cluster into two groups. So the first group consists of problems whose solution time are bounded by polynomial of small degree, and the second group is made up of problem whose best known algorithm are non-polynomial. So the theory of NP completeness which we present here does not provide a method of obtaining polynomial time algorithm for problems in the second group, nor does it say that algorithm for of this complexity do not exist. So instead what we do is show that many of the problems for which there are no known polynomial time algorithm are computationally related. So in fact we established two classes of problem. These are given names NP hard and NP complete. So there are two names given, that is NP hard and NP complete. So a problem that is NP complete has the property that it can be solved in polynomial time if and only if all other NP complete problems have been solved in a polynomial time. And if an NP hard problem can be solved in a polynomial time, then the NP complete problem can be solved in a polynomial time. So before me moving with, let me tell you, P stands for polynomial time. So P is a set of all decision problems solvable by a deterministic algorithm in polynomial time. Remember, this is very important. P is a set of all decision problems solvable by a deterministic algorithm in polynomial time, and NP stands for non-polynomial. So NP is a set of all decision problem solvable by non-deterministic algorithm in polynomial time. Now let us see what is NP hard. A problem is in the classes of NPC if it is NP and is hard as any problem in NP. So the problem is NP hard if all the problems in NP are polynomial time reducible to it, even though it cannot be in NP itself. In short, a problem L is NP hard if and only if it is satisfiably reduces to L. Next we will see the diagram. It shows the diagram having the classes of NP, NP, NP complete and NP hard. So here you can see in this figure that although one can define any distinct problem classes having the properties stated above by an NP hard and NP complete classes, then we study are related to non-deterministic computation. So we see that the classes of NP hard problem is very rich as it contains many interesting problems for a wide variety of disciplines. So first we have to formalize the proceedings about the classes. So here in this figure they have shown that there is a P class that is a polynomial time, and having an NP class that is non-polynomial time bounded with another classes. So the combination between the classes having P and NP is segregated into a separate part with the classes of NP hard and NP complete. So in this figure you may see that there is a class of NP complete and NP hard merged for a fewer part, and which is shown in the figure with a dark section. So this part is called as NP complete, and whereas the remaining part is called as an NP hard. So this figure shows the satisfiability is in P if and only if P is equal to NP. So this is the formulation of a Cook's theorem, and it is easy to see that there are NP hard problems that are not NP complete problem. So only a decision problem can be NP complete. However, an optimization problem may be NP hard. An optimization problem cannot be NP complete. So there also exists NP hard decision problem that are not NP complete. So decision problems can both NP complete and NP hard. So if L1 is a decision problem and L2 is an optimization problem, then it is quite possible that L1 is inversely proportional to L2. Above figure shows an example that it is satisfiability is in P if and only if P is equal to NP, and this type of explanation can be also applicable to the Cook's theorem. Next we will see what is NP complete. So as we have seen, NP hard, a problem L is NP hard if and only if satisfiability reduces to L. So now in an NP complete, a problem L is NP complete if and only if L is NP hard and L belongs to NP. So like we have seen in a diagram itself, NP complete belongs to the problem of NP hard. So if the L is NP complete and if and only if L is NP hard, then L belongs to an NP. So this is type is called as NP complete. So if a polynomial time algorithm exists for any of this problem, all the problems in NP would be polynomial time solvable. These problems are called as NP complete. So the phenomena of NP completeness is important for both theoretical and a practical reason. So till now we have seen what is P, what is NP, what is NP hard, and what is NP complete, and relationship between P and NP classes. Next we have a definition of NP completeness. Now here it has been shown that a language B is NP complete if it satisfies two conditions. Now let us see what are those two conditions. These are B is an NP and every A in NP is a polynomial time reducible to B. So these are the two conditions where we can say that the B is NP complete, that satisfies this condition. So if a language satisfies the second property but not necessarily the first one, then the language B is known as NP hard. And informally, a search problem B is NP hard if there exists some NP complete problem A that Turing reduces to B. So the problem in NP hard cannot be solved in polynomial time until P is equal to NP. As we have seen in the previous Venn diagram, that satisfiability is in P if and only if P is equal to NP. So the problem in NP hard cannot be solved in polynomial time until P is equal to NP. So if a problem is proved to be NPC, there is no need to waste time on trying to find an efficient algorithm for it. So instead we can focus on design approximation algorithm. So the NP complete problems is following are some NP complete problem, like determining whether a graph has an Hamilton cycle and determining whether a Boolean formulation is satisfiable. So these are the NP complete problem for which no polynomial time algorithm is known. Next we have see that what are the NP hard problems. So the NP hard problems are circuit satisfiability problem, set cover, vertex cover, traveling salesman problem. We will discuss it into next slides what is traveling salesman problem. So the NP hard graph problems are clique decision problem, node cover decision problem, chromatic number decision problem, directed Hamilton cycle, and or graphs, and traveling salesman decision problem. So these are the 6 NP hard graph problem. We will see it one by one. So the first is clique decision problem. So a clique, basically it is a subgraph of a graph such that all the vertices in this graph are connected with each other. That is, subgraph is a complete graph. So the maximal clique problem is to find the maximum sized clique of the given graph G. That is complete graph which is a subgraph of G and contains the maximum number of vertices. So this is an optimization problem. Correspondingly, the clique decision problem is to find if clique size k exists in given graph or not. So here in this side you see that there are the graph shown having vertices and edges. Vertices is marked in a green color, that we call it as a node. So here in the first diagram you see that there is a graph having a cycle vertices of node 1 to node 2 and node 3. Node 1, node 2, node 3 having one cycle, that it indicates one graph diagram. So we will call it as a clique of size 3. Now another node has number 4 and 5. Now 4 and 5 can be defined as another graph. So it can be stated as clique of size 2. If any of a graph having a subgraph, then we will be considering that subgraph with a clique and clique of size whatever the size will be. So this is how the above graph having contains a maximum clique of size 3. In figure 2 there is an another graph, and here there are total 5 vertex 1 2 3 4 and 5. So now node 1 to node 4, like node 1 2 3 and 4, it contains one subgraph having clique of size 4. Size 4 because there the number of nodes are 4. Next we have another subgraph having 5 3 and 4. So these the another subgraph will be having clique size of 3. So the maximum clique size in this total graph is 4, because there are number of 4 vertices which create another subgraph. So we will be defining that as clique of size 4 or clique of size 3. So this is how clique decision problem is. Next we will see node cover decision problem. So a vertex cover of an undirected graph is a subset of its vertices such that for every edge u comma v of the graph, either u or v is in the vertex cover. So although the name is vertex cover, the set covers all edges of the given graph. Given an undirected graph, the vertex cover problem is to find minimum size vertex cover. So let us see with an example. So here in this example, the first minimum vertex cover is empty because there is no vertex covered with each other. So 0 and 1 does not bounded with each other. Hence we will mark it as a minimum vertex cover is empty, 0. In this next section, medium graph, there are total 4 vertices, but only 3 vertices are connected to each other. Like there are 4 nodes 0 1 2 and 3, but there are total 3 vertex. So the minimum vertex cover is 3. In the last graph there are total node 5 0 1 2 3 5 4, but here in this case the minimum vertex cover is 4 and 2, like 4 because if total number of nodes are connected, and if we see if there is complete cover between the nodes or not, then we will see that there are 2 nodes which are corresponding to each other. So the minimum vertex will be 4 comma 2 or 4 comma 0. Next we have chromatic decision problem. Now in chromatic decision problem, you may see that there is a graph shown. In that chromatic decision problem, a coloring of a graph, suppose g v comma a is a function like f v tends to 1 to k. Now define all I belonging to v. So if u comma v is belonging to a, then f of u is not equal to f of v. Like if there are some edges and some vertexes, so if u comma v belongs to that edges, then function u is not equal to function v, and no two adjacent nodes have same color. Now in this case, if any of the two adjacents have same color, then they will not belong to each other. So in this problem, no two adjacent nodes should have a same color, and the chromatic node decision problem is to determine whether G has coloring for a given K. Now suppose there are K number of vertices. Now every node should have some coloring, some equal coloring. So we have to find that, or to determine that whether G has a coloring for a given K, and if it is so, then CNP is an NP hard problem. So now in this graph, possibly two coloring of graph is f1 function 1 is equal to function 3 is equal to function 5 is 1, and function 2 is equal to function 4 is 2. Like function 1, that is vertex 1, vertex 3 and vertex 5 have same color, so we will marking it as an 1, and function 2 and function 4 have different color, so we will be marking as a 2. So this is how the chromatic number decision problem is. Next we will see TSP is NP complete. TSP stands for traveling salesman problem. So the traveling salesman problem consists of a salesman and a set of cities. So now there will be one salesman and there will be number of cities, and the salesman has to visit each one of the city starting from a certain one and returning to the same city. So now suppose there are total 4 cities like Kolhapur, Pune, Mumbai and Nashik, and there is one salesperson. So if the salesperson is starting the tour from Kolhapur, visiting to Pune, then Mumbai, then Nashik, then he has to return to Kolhapur. Like he has to return to the same city from which he has started. So the challenge of a problem is that the traveling salesman wants to minimize the total length of the trip. So this is the problem of traveling salesman. So now let us see the traveling salesman problem is NP complete. So to prove that traveling salesman problem is NP complete, first we have to prove that traveling salesman problem belongs to NP. So in TSP, we find a tour and check the tour contains every vertex once. So that now, as I said, there are 4 cities and one salesperson. Now that salesperson have to visit every city only once. If he is visiting twice or thrice, then it will be not considered as a traveling salesman and NP complete problem. So that person has to visit Kolhapur once, Pune once, Mumbai once and Nashik one time. So if the person is visiting Mumbai twice or Pune twice, then it won't be considered into an NP complete. So we have to find a tour and check that tour containing every vertex once. So then the total cost of the edges of the tour is calculated, and finally we check if the cost is minimum or maximum. If the cost is minimum, then we will be considering that cost. So this can be completed in polynomial time, and thus TSP belongs to NP. And secondly, we have to prove that TSP is a NP hard. So to prove this, one way is to show that Hamilton cycle is less than equal to TSP. As we know that Hamilton cycle problem is an NP complete. So assume there is a graph having vertices and edges, G is equal to V comma E, to be an instance of Hamilton cycle. So hence an instance of TSP is constructed. We create the complete graph G dash V comma E dash, where E dash belongs to I comma J. I and J are the adjacent nodes and that are belonging to the E. So thus the cost function is defined as Tij 1 if Ij belongs to otherwise. So like if there is a vertices between the city 1 to another city 2, like if there is a connection between Kolhapur and Pune, then we will be marking it as a 1. If there is no connection between Kolhapur and Pune, we will be marking as a 0. So this is how we will be calculating the traveling salesperson problem. Now suppose that a Hamilton cycle H exists in G. It is clear that the cost of each G is H is 0 and G dash as each belongs to E. So therefore H has a cost 0, and thus if graph G has Hamilton cycle, then the G dash has a tour of 0 cost. Conversely, we assume that G dash has a tour H dash of a cost at most 0 and the cost of edges E are 0 and 1 by definition. So hence each edge must have a cost of 0 as a cost of H dash is 0. We therefore conclude that H dash contains only edges in E. So we have thus proven that G has a Hamilton cycle if and only if G dash has a tour of cost at most 0. So we will say that traveling salesperson problem is a NP complete problem. So till now we have seen the problems such as clique decision problem, node cover decision problem, chromatic decision problem, directed Hamilton cycle and traveling salesperson decision problem. So all these problems comes under NP hard graph problem. And we have proved that every problem comes either under NP hard or NP complete classes. So this PPT shows that what are the classes of P that are NP complete classes, NP hard classes, and which problems comes under NP hard problems and NP complete problems. I hope you have been clear with this session. If you have any doubts, please feel to contact me. Thank you.